Well, good morning, everybody. Just for starters, I looked over quiz one, graded all the short answer questions, so you should be able to see your grade for that. Please let me know if you have any questions there. This Friday is the formal kind of a day which assignment one will be assigned. I will be posting a little video talking about that in the next couple of days. I'll mention this again on class on Thursday. So that's coming up. All right, so what we're going to do now is jump into new material. Chapter 2 was essentially an overview in some sense of the general ideas of machine learning, and then chapters 4 and 6 were hopefully not entirely new, even though regularization may have been new as a topic, but just the idea of linear regression in general hopefully is something you've seen before. But now we're going to get into material that I figure for most people is probably new, although you may have seen a little bit of it in some other course, but I'm not assuming any of that. And this is, in some sense, the core kind of the course, at least one of the two real main core areas, which are what we call tree-based mathematical machine learning methods. And when I say it's the core of the course, it's because it's the next 4 chapters, chapters 9 through 12, all deal with these ideas in some form or another. So it occupies quite a bit of time in the course. The other really core topic is chapter 13, which we'll talk about much later and is much different. Okay. But the idea is that there's a particular approach to building certain kinds of models, which is very useful as a predictive machine learning technique. And so what we're going to do in chapter 9 is introduce the basic idea. And then as we'll see in chapters 10, 11, and 12, we're going to build off of that basic idea to create more powerful models essentially through aggregation. So chapter 9 deals with the topic of what are called decision trees. All right, so what do we mean when we talk about tree-based models? Well, these are an example of what we call non-parametric algorithms. And what this means essentially is that at the start of the process, the algorithm doesn't make essentially an assumption, a strong assumption about what the model should look like. Okay. So they don't make strong assumptions about the functional form of the model. And an example of such a model, a non-parametric algorithm, is the one we briefly talked about, KNN. What we're saying is that the algorithm doesn't assume at the start a particular structure for how it takes the features and generates a target prediction. Okay. And then a non-example, which we've also talked about. In other words, what's something that's not a non-parametric algorithm? In other words, a parametric algorithm, linear regression. So what we mean here is that when we say linear regression is a parametric algorithm, well, to say what a prediction looks like from a linear regression model, we know exactly what it's going to do. Y hat, the target prediction, is given by a functional application to the target x, or sort of the features x, and it's given by a formula that we can even write down, right? So it's given by taking the individual features, multiplying them by coefficients, adding a constant, and then you have an error term. The point is that we can essentially write down an algebraic formula which describes exactly how the model is going to take features and generate predictions. Okay. So with tree-based models, we aren't going to have this. We're not going to have some kind of explicit functional form like this. Okay. What tree-based models do, in some sense, they model and they make predictions in kind of the same way that you might expect, say, naively expect a computer algorithm to, say, solve a game like a chess problem, right? Where at any given step, it evaluates as many or all perhaps possibilities and figures out which one's the best in some sense, measures them, it gives some kind of value measurement to which is the best play or best move, and then it picks that one. Now, that's not exactly how chess algorithms or other game algorithms work, especially in the modern context, but it's the rough right idea. And so tree-based models actually do something kind of similar. So what they do to make their predictions is they build what's called a tree diagram. By partitioning on the features in a step-by-step way, using what we're going to call splitting rules. Now, all these terms, we're going to define them carefully. So what do you mean by a splitting rule? What do we mean by a tree diagram? What do we mean by partitioning, and so on? Partitioning on the features. Maybe we'll put that in quotes as well. So these are all things we're going to explain. Okay. There's a sense in which, at its core, a tree model has a similarity to KNN in the sense that what it's doing is it's breaking up the feature space by similarity, right? So the sections of the feature space are partitioned based on similarity in the response values. Now, we need a formal, precise way to say what we mean by response values being similar, and we're going to have that. Not surprisingly, we're going to use a loss function to measure that. And the idea is that we're splitting up, and then what we're going to do to make a prediction on a particular region is fairly straightforward. Okay. So then we fit a simple predictive model to each region. So we split up the feature space by similarity in response values in some way. And then for each of those regions that we were saying are similar, we make a prediction off of that region. So what's one way you can do this? Take the average, if it's a numerical problem, if it's a regression problem, take the average response value in that region. So this is what we mean by a simple model. So we have a region in this feature space. All we're going to do is just average together the targets, right? So average response value in each region. That'd be one simple approach. And that's actually what we are going to want to do for regression problems. Now, there's also, of course, classification problems, and we need another approach there because we don't have averages. But similarly, the approach is pretty simple in the sense of what we're going to do. And we'll get to that a little later. Okay, so there's kind of a generic description of what tree-based models are like. Let's start going through the process of formalizing these concepts that we're introducing here, and these kind of ideas and words that I've introduced to talk about these. So what do we mean by a tree diagram? one of the nice things with tree-based models, decision trees as we're going to call them, is that we can visualize what's going on, how the model is working, and how decisions are being made. Okay. So these are tree diagrams are visualizations of what we call the splitting rules. I.e., the decisions the algorithm is making. The decisions, or you can think of them as choices. So the algorithm is going to assess all sorts of possibilities, and then what it's going to do is it's going to try to pick the best one. Okay. So that's essentially the general approach that we're going to use here. So decisions, algorithm is making. Okay, so here is what a decision tree looks like. So this example in this picture that I've just tried to, oh, and it's not loading, is it? You guys, you can't see that image, right? It's all blank. Okay, this is weird. I wonder, it's never had this problem with these before. Let me try the other one just to see, is it just one file that's messing up? No, that's not working either. This just became a problem the other day. This is not good. You know what I'm going to do is I'm going to open them in Chrome and share them. Okay, that'll hopefully work. Let's try that instead. Oh. No, I can't. Or let me see if I can just share the window. Let's try this. Okay, I can't open them in Chrome, but I can open them in another file. Window, yeah. Is that showing up now? Okay, good. We'll have to do it that way, and I'll see something's wrong with Collaborate, or at least something's weird's going on. Okay. So this uses one of the standard data sets in the textbook, which is a classification problem related to whether or not a customer will redeem a coupon at a store. So the idea here is this model is trying to, what it's doing in this decision tree is it's trying to decide what's the best way to determine at each individual step, what's the best way to determine to break customers into yes and no groups, right? As many as possible in each. So what's happening on the first split is what the model has determined is that the single best way to determine whether somebody is going to redeem a coupon or not is, are they a loyal customer, yes or no? Okay. Then at what happens next is it says, okay, now that we've determined that's our best way to split into do they redeem a coupon? At the next level, we're going to try to find the next best way to split them up, to determine whether or not they redeem a coupon. The idea is at the bottom, you want to have as many people as possible in each part, okay? In the yeses and the nos. So for instance, all right, if they are a loyal customer, what the algorithm figures out is that the next best predictor as to whether they will yes or no redeem a coupon is household income, whether it's greater than or less than 150K. On the other hand, if they are not a loyal customer, the best predictor as to whether or not they will or won't redeem a coupon is last month's spending, whether it's greater than $100 or less than $100. Okay, and then there's another split at the next level, although notice it's not necessarily consistent. In some cases, there's a split, in some there's not. You might ask why. Well, we'll see later that sometimes you stop splitting. The algorithm will stop making more splits if you tell it to, based on essentially assessments of how well it's doing, how accurate it is, how the loss function is behaving, and so on. Okay. So the idea then is the algorithm, once it's done training and it's stopped essentially doing these splits, creating this diagram, at the bottom you'll have essentially response values. So notice at the bottom level there's all yeses and nos. Basically the idea is as you follow the tree down, which is we're trying to indicate on the right, you end up at the bottom, and it gives you a prediction, a target prediction. So for instance, what the version on the right, where we've kind of blotted some of it out and only highlighted part of it, what this is trying to say is, what the algorithm is predicting is that if you have a loyal customer whose household income is greater than 150K and they shop in store, then yes, they will redeem a coupon. That's what the algorithm would predict for in some sense. What do we mean by a region in the feature space? We mean a customer with a particular profile, right? So all customers that have that profile, it would predict they're going to do this. In this case, redeem a coupon. So that's the idea behind how a decision tree works visually. It represents the process of the algorithm making a prediction by a step-by-step, these step-by-step splits. Notice that the first variable is a qualitative one. Are they a loyal customer, yes or no? The next couple in the split are quantitative. Last month's spending and household income are given numerically. But also notice, and then say shopping mode is qualitative. It's online, so online or in store. But at the end of the day, everything can be broken down into yes or no questions, right? So even a quantitative variable, a numerical one, can be thought of as splitting on a yes or no question. In this case, on an inequality, right? Greater than 150K or less than 150K, that's a yes or no split. Is it greater or not? So we're always doing, this is a binary process. There's always just two possibilities. Okay, so going back and then describing what's going on here. All right, so as that kind of image was meant to indicate, so the example just seen should give, hopefully, the impression that decision trees are relatively simple predictive models. In the sense that for an individual decision tree like we looked at, there's not a whole lot going on, right? We're answering a few yes or no questions based on, well, something that's lurking in the background that we'll eventually talk about, how we're assessing the model performance. Okay. But we're just answering a few yes or no questions, and then off of that making a prediction. And so as a consequence, an individual decision tree like that is a fairly simple, not particularly powerful modeling approach. Okay, but this is what's really nice about them. They can be combined. So if we have individual decision trees like this in various ways, to produce powerful, what we call ensemble algorithms. By taking this relatively simple basic algorithm, we'll refer to eventually as a base learner, the individual decision trees. I can't realize this. What we'll see is that by combining those in various ways, aggregating them together, we get extremely powerful methods. One of these is called random forests. This is what we'll talk about in chapter 11. And another is called gradient boosting machines. And this is what we'll talk about in chapter 12. And these, as it turns out, are two of the most powerful machine learning methods overall. There's various sort of machine learning competitions. You might have heard of a website called Kaggle, if you haven't, Kaggle. We'll talk about, I'll mention it at some point in chapter 12. It's a way of essentially competing with other people to see how well you can program machine learning algorithms. And gradient boosting machines tend to be one of the techniques that essentially produces the best results on those competitions. The other really powerful technique that we'll talk about in chapter 13, or at least scratch the surface of, are neural networks, but that's a completely different beast, and as we'll see. For the kind of basic, you might say, modeling problems we're going to talk about in this course, and the kind of thing you might even do in the project course, these two approaches, random forest and gradient boosting machines, are often going to be your best bets. Okay, so a little preview of sort of what's to come. We're going to build off of something very simple like we just looked at, that models of the same type as that picture. And from that, we're going to eventually arrive at very powerful techniques. Okay, so with that in mind, we want to describe what is the basic decision tree in a formal sense, and how are we assessing how well it's doing. Okay. So there are, as it turns out, a few approaches algorithmically in terms of how they're programmed and so on, to even the basic decision trees. But by far the most standard is, and this is what we're going to talk about, what's called CART, C-A-R-T. And this is what you may have heard of depending on which courses you've taken of, like, say, STAT 310 and 311. This sometimes will come up. And so CART stands for classification and regression tree. And so as the name suggests, this approach can handle both classification and regression problems, which is great. So we've got one kind of framework. We don't have to describe both types. The big difference, as we'll see, is, well, what kind of loss function we're going to use. We obviously can't use the same loss function for a regression problem and for a classification problem. All right. So what does the CART process look like? It looks like what we just saw in the previous picture. We start with all of our training data. And then we split up that data into two regions. And then we split those two regions up individually into, say, perhaps two more regions each. And this process continues. We keep splitting until we've decided that we're going to stop. And so what these different regions here consist of as are observations from the data in the feature space. And we call these nodes. So the idea is what we're trying to do is we're trying to group together observations in the data where the responses are as similar as possible. And that's formally speaking. So when we talk about nodes, we're talking about subgroupings or subgroups of the data which are as homogeneous, so just a fancy way of saying similar in this sense, so homogeneous as possible by their response values. So going back for one moment to the previous, the example image, to kind of give an idea here of what we mean by that. So if we think about the split, loyal customer, yes or no, that being the first split, what that's telling us is, now, it's probably not the case. We certainly wouldn't expect it to be the case that, say, all loyal customers redeem coupons and all non-loyal customers don't, right? There's no reason to expect that the targets values are perfectly split on that one split into yes, all yes on one side and all no on the other. But the idea is, based on however the algorithm is assessing things in the background, that split on loyal customer, on the answer there, is the one that does the single best job of having the next two nodes be as homogeneous as possible. In one of those, there's as many yeses as possible. In the other, there's as many no's as possible, say, right? It does the best job of kind of splitting that up in some form of sort of purity, as we might describe in the note. Okay. That's essentially the idea. Now, it's if it was a regression problem, the idea would be that we'd assess using, say, root mean square error, and the idea would be the difference in response values at the two nodes is as small as possible by that. Okay, so this is the idea, is that on that one split, at the next level down, we group together a bunch of observations, and the target values of those observations are as similar as we can make them. And then the same thing proceeds at the next split and the next one, and so on. So that's what we mean by saying as homogeneous as possible by response values. Okay, so how does this happen? So here's the next place we're going to start trying to carefully define some of these terms. So CART, this algorithm that does this, uses what we call recursive binary partitioning. So we say, or is a recursive binary partition. All right, so there's three terms here. I've underlined them each individually because what we want to do is we want to define each of them. Right. So binary, actually, I already described what the point is here, is that every split can be viewed as a yes or no question. Right? It's going to be viewed as you're answering a yes or no question. Yes goes one direction, no goes the other. And as mentioned, if you've got a binary variable already, a categorical variable, so something where you can just think of it as yes or no questions, then that's clear. If you have a multinomial classification, then essentially what you're going to do is you're going to say, okay, pick one of the classes, whichever one it is you sort of care about. Are they in that class, yes or no, right? So you're essentially creating, from a multinomial, you're going to binary by subdividing everything. So if you're classifying on, say, on colors or something like that, you're going to ask, is it blue, yes or no? Okay. And if it's numerical, as I already mentioned, how do you reduce a numerical variable to a yes or no question? By splitting on an inequality. And so that's essentially how it will always work for those. Does it satisfy the inequality, yes or no? That's an unambiguous question that you can be answered that way. Recursive, what this refers to is that the splits depend on the previous ones. We actually saw that. I'm not going to bring the example picture up again, but you can always open it if you've downloaded it from the Moodle page. But if you look at it, if you do have it open, or you go back and take a look at it, so after the first split, loyal customer, yes or no, the next split, the choice of variable and what the split was on depended. It changed. So if the answer was no, then the split was on last month's spending, whether it was greater or less than $100. And if the answer to loyal customer is yes, it was on household income, whether it was greater or less than 150K. And so that's what we mean by the splits depend on the previous splits. You don't have to be splitting on the same variable just because you're at the same level. It also depends on where you've gone before. Okay. And finally, when we say partition, did I misspell it up here too? Yeah, it is. It was so partitioning, not partitioning. Partitioning. Sorry about that. Okay, so we say partition. This means is that the data is divided into non-overlapping regions. And this is because given a data observation and its target value, when we ask a yes or no question, that's unambiguous. The answer is either yes or no. It can't possibly be both at the same time. When we ask about, okay, so is the household income greater than 150,000 or less than 150,000? It's not both greater and less than 150,000. Are they a loyal customer? Yes or no? That's an unambiguous question. There's one answer. Okay. So then the point then as this is that at the bottom level, which we're going to give a name to a little later, Enrique in the chat asked, is Schrodinger's cat alive? For those of you who don't know this is a reference to a classic question, motivating idea, philosophical idea in quantum physics or quantum mechanics, which is the whether a cat is alive or dead if it's in a box and you can't see into, and there's a radioactive element in the box that may or may not decay and kill the cat. Okay. So yeah, we don't have to, with this at least, we don't have to deal with any kind of ambiguous question like that. Hold on to that kind of thought for a while. Not that we're really going to ever get back to it, but when we talk about neural networks, well, we're just, like I said, we're going to scratch the surface of the idea in chapter 13. Actually, the surface is still going to take 3 weeks. But we're going to look at like sort of the most basic idea. Well, something that people are trying to work out and something that I'm actually interested in, we're called quantum neural networks, where you try to replace the classical neural network structure that we're going to describe with a quantum structure, which is extremely difficult to figure out how to do from the reading I've done at least. Anyway, it's won't get too far afield here. So we don't need to deal with any quantum uncertainty when we're talking about decision trees. Things are not alive and dead at the same time. So at the bottom level of the tree, every point in the training data is in exactly one node. So at the bottom of the tree, then where the nodes you have, any point in the training data will be in exactly one of them. Because every point in the training data has answers to these yes or no questions, and it doesn't have the 2 different answers to a yes or no question, so it can't go down 2 different branches. Now, as we'll see, it's possible at the bottom that some of the nodes don't have any training data in them. They can be empty if there's no training data that fits that description. Okay. But the actual data itself, every point kind of moves down the tree to one position at the end. All right. So at some point, this binary recursive partitioning process stops. Can't spell partitioning today to save my life. Okay. All right. So how do we know why in the example did we only go say 3 splits down with the coupon example, or in some cases only 2 down and then stopped, right? There was only 2 splits on one side of it. Okay. So we have to have some idea why is this happening, or how are we deciding when it happens? And the concept here is what's called depth. Okay. So the depth of a tree is the maximum number of splitting levels. Okay. So equivalently, if you like, the number of times yes/no questions are asked. Okay, so of course, I closed it. Now I need to bring it up again. So just coming back to our example again that we were looking at. Let's. So this is a depth 3 decision tree. There's a maximum of 3 splits, right? So say going down the right-hand side, we say loyal customer, yes. Household income greater than 150K, yes. Shopping mode, store. Okay, and then that. So there's 3 splits, and then there's one more sort of level, right? Like we go down to the bottom. Equivalently, there's 3 levels below the training data, below the first split. So this would be a depth 3 decision tree. We do 3 splitting questions, and then that generates the nodes at the bottom. Okay. Even though, say, on the left-hand edge, there's only 2 splits before we get to the bottom, right? The maximum, the depth is the maximum number of splits that would take us to the bottom. And in this case, that's 3, depending on which path we're taking. Okay, so when we get to the bottom of the tree, how are we making the predictions? So this is a predictive model. We're trying to get target predictions. So the predicted target value given by a decision tree for a given feature, given point in the feature space. So in other words, if you input an observation, a set of feature values, what does it produce as the target prediction? Well, of course, it depends on whether we have a regression or classification problem. In other words, are we dealing with numerical target data or categorical target data? But in both cases, the way we do the prediction is fairly straightforward. Okay, so for regression, it's exactly what I described earlier. You simply take the average. We'll say that in a little more formal language. So the idea is take the mean, right, so average, response value, for target value, add a node, then use this for the prediction, the predicted target value for any point that would end up in that node. Okay, so what I mean here is we ran the algorithm on the training data and created this tree. And so suppose we then feed in a data point where we want a prediction. What the algorithm does is it figures out, okay, well, which one of the nodes at the bottom would that data point land in based on the feature values. And then what it does, it says, oh, okay, it ends up in this node. Therefore, I'm going to take all the response values in that node, average them together, and that's what I would predict it would have as its response value. So that's how it works for regression. Simply taking an average of all the information you already know, the target values that you have at a given node. What about for classification? So there's two basic options here. One is to simply predict classes, make an unambiguous prediction like yes or no, they're going to redeem a coupon. The other is to introduce a little more subtlety by creating a probabilistic prediction. So what the first possibility is predict classes. Now there's two approaches here, in fact, so two sub-approaches. So using either well, one is just majority, what we call majority vote or majority representation. And this will certainly work for binary. Okay? It will always work for binary because you only have two possibilities. I guess, okay, you could have a tie. So then you have to have some way to resolve that. So the idea here is, suppose at the bottom of the tree, we end up in a node in the yes, say the redeem a coupon example. Yes or no. So if there's more yeses than nos at that node, the algorithm predicts yes. And if there's more nos than yeses, the algorithm predicts no. That's very simple. Now, if you're doing multinomial classification, like say we're trying to classify, I've mentioned this example before that we'll talk about at some point, not here, but later in the course, about trying to classify digits, doing digit recognition, right? So there you've got 10 possibilities, 0, 1 through 9, and you're trying to predict, oh, does this shape, which one of these digits is it, okay? Well, it could be that there isn't a majority representation. There's only plurality. So when we say plurality vote or representation, even if one of them is not a majority, we simply take the one that has the most. So if we end up at the bottom in a node and there's more 9s there than any other digit, even if it's not the majority of them are 9s, maybe only 20% of them are 9s, but nothing else is better than 20%, that's what we would predict would be 9. So, oh, is this one on the quiz questions? I'll double check that. I'm not sure if it should have been in that section. I think it is discussed in the text when we in the context of how to do multinomial versus binary classification in chapter 1. But let me double check that. That was more of a question for kind of later. I might not have meant to include that one. So yeah, because I didn't talk. So sorry if that was on the quiz. I'll double check. Sorry about that, and make a comment on that later. Yeah. So this is, and we'll come back to this idea as well at other points. But then the other thing we can do is make probabilistic predictions. So we said predict classes, and the second possibility is predict class probabilities. So this gives a more subtle type of prediction and one that perhaps is a little more flexible. So the idea here is use the class proportions at the end, so at the final nodes, at each node, so to give probabilistic predictions. And what's nice about this is that it allows you to hedge a bit, to be a little more kind of subtle about you're not just making an unambiguous prediction, this or this class or that class. And it's also quite useful because you can do it for both binary and multinomial classifications. Okay, so let me just as an example of what I mean. Suppose we end up at a node at the bottom, and we're just answering a yes or no, so a binary classification problem. And in that node, there are 60 yes answers and 40 no answers. So then what we would do is we would predict that the probability of a yes is 0.6 and the probability of a no is 0.4. Or another example, suppose we end up at the bottom and we're doing a multinomial classification and we have 3 categories, A, B, and C. And A contains 15, there are 15 A's, 23 B's, and 31 C's. Okay. So then what's the probability predicted for A? it's 15 out of, and then what do we have here? 69. And then the probability of B would be 23 out of 69. And the probability of C would be 31 out of 69. So this is a nice flexibility that you get if you use probabilistic predictions. You can simply, it works either way for binary or multinomial classification. So in the first example, so let me call these, let's call this one part 1 and part 2, just so I can refer to them. So with the probabilistic prediction, so in 1, majority vote would predict yes. Okay. So if we're, instead of using probabilities, we're simply trying to make unambiguous predictions, that's what we would get. And in 2, so here notice none of them have a majority, right? Because there are 69 data entries at that, there's 69 observations at that node, and none of these have more than half of them. But so here, plurality vote, what we're looking for is simply the one where there's the most. It would predict C. Okay, so that's the how majority vote and plurality vote would work in these sorts of situations. And in particular, for 2, we can't use majority vote because there isn't a majority, right? And that's why when doing multinomial classification, you need to relax that to plurality. Okay, so where are we making these predictions? We're making them at the nodes that occur at the bottom of the tree. And it would be nice to have some terminology that's a little faster to say than the nodes at the bottom of the tree. Okay. So here's we're going to introduce some terminology for decision trees. I'll write it out, and then we'll look at a picture just describing it. So in all cases, both regression and classification, we make these predictions for the nodes at the bottom of the tree. And these are called, so with decision trees and related topics, we use lots of tree kind of based terminology. So things that are designed to evoke the image of an actual tree. So we call these leaves or leaf nodes. Or sometimes if we don't want to use tree terminology and we want to use something that's more computer sciencey, we would say, or terminal nodes. So these all mean the same thing. So the node for the initial split, before we've actually split on the data, okay, so there when we make the initial split, we're using all the training data. So this node, which consists of all the training data, is called the root node. So hence, it's the root of the tree, right? The root system, so to speak. You can see it's another sort of tree type name. Nodes sort of inside the tree, so between the root node and the terminal node, are called, we don't have a kind of a tree-based name here, we just call these internal nodes. I'm not sure what the equivalent thing for a tree would be, right? Like maybe knots or something like that, where like, I don't know, where the tree sort of I don't know what you call them where it branches off, but nodes are connected to other nodes. Here, the name makes sense, by branches. So the branches are just simply the lines indicating the splits that are happening. Another kind of tree-based name. Okay. All right. So here's an image then of this terminology at play. Basically, right, it looks like a tree that's upside down. Because of course, with an actual tree in the ground, the roots at the bottom, right, the ground, and then the tree grows up to the branches, through the branches, eventually to the leaves at the top. Say. All right. Well, we just do it the other way around because you kind of think about it more like a flow chart, the way a computer algorithm would work. You start at the top and simply move down it. So we begin at the root node, and then the branches are representing the different splits. The nodes in between are the internal nodes, and then finally at the bottom we have the leaf nodes or terminal nodes, and those are what we're going to make our predictions off. Okay. So how do we go about the process of partitioning? How are we making these splits? So just as already mentioned, so in CART, in this algorithm, the partitioning is recursive, which, just as a reminder, what that meant was the splitting rules at each level the splitting rules chosen at each sort of level in the tree depend on all the splits above. Okay, so specifically, what's going on then? At each node, we determine the feature variable let's just say for the moment that it's, say, xj for some j, that gives the best partition of that node into two disjoint, here disjoint meaning no overlap, regions. Call them R1 and R2. It'll be helpful to have some notation around here in a minute. So we split into these two regions, R1 and R2, which will become nodes at the next level, which become nodes at the next level down. So in other words, we have a branch from the node we're at to each of R1 and R2. Okay, so anytime when we describe a process like this, and we use a word like best, especially when we put it in quotes like this, the immediate question is, how are we defining that, right? How are we determining it? So, oops. And the answer is through loss functions. All right, so of course, it depends on what kind of modeling problem we have, what kind of loss function we're going to use. So the choice of loss function then depends on what kind of problem we're dealing with. the choice of loss function depends on the type of problem. So not too shockingly for regression, we're going to do some version of sum of squares error. Okay. So what we're going to do is we're going to minimize the sum of squares error at each split. And then, well, for the at the very end, if we wanted to say get to measure, say, the generalization error, then we'd probably use root mean square error so that it's in the same units as the original data. But the idea is that as we're going through the tree, through the splitting process, we don't need to actually compute, say, the root mean square error. All we need to do is compute the sum of squares error and minimize that, because then the corresponding root mean square error will also be minimized. Okay. So what we're doing, so here's the notation. The sum of squares error in this case, how are we measuring it at each node? What we're doing is we're taking the sum over all response values yj that are in region 1, and then we're taking, we'll say, yj minus, I'm going to call it C1. I'm going to define these in a moment. Okay. C1 squared, and summing all of those up. And then we're going to take the sum over all yj's in region 2, and we're going to take yj, so the response values minus the number C2, and square those, and then add that up, and then we're going to add those all together and get the total sum of squares error. Okay. So where for k equals 1 and 2, what do I mean by C sub k? Okay. This is the average response value, or target value, whatever term you like to use, for all data points in region RK. So in other words, we've split into region 1 and region 2. And we take all the data points in region 1 and we average the response values to get C1. And then for each individual data target value in region 1, we take the difference between that and the average. Essentially what we're doing is we're measuring deviations away from the mean, right? And then we square those up and then add them all up. And then similarly for region 2. Okay, so the idea is that at each split, what we're going to do is we're going to try to figure out how to divide into region 1 and region 2 to make this total sum of squares error the smallest as possible. Okay. Now for classification, what we want to do is we want to maximize the reduction in a loss function. So the idea here is we're going to have a loss function, and what we're going to want to do, it's a loss function where what we're going to try to do is make it go down by as much as possible. And there's two real main choices here that get used. Okay. Specifically, either, and I'd mentioned both of these before, but said we would wait and talk about them, and now we are going to talk about them. It's called cross entropy, or the Gini index. Yeah. All right. So I did mention we were talking about classification loss functions. These were two approaches used with tree-based methods, and we talked about them in chapter 9, hence now. Okay, so what are they? Okay, so what's cross entropy? Sometimes this is also just called entropy. All right, so we'll denote it by capital E. What we do is we take the sum, say from j equals 1 to n, so overall data points, And then we take the following quantity. Negative of p sub j base 2 log of p sub j. Okay, let me tell you what p sub j is. Where p sub j is the probability of classifying a data point into class J. So in other words, the n here is the number of different classes. So if this is a binary question, that's the sum from j equals 1 to 2. But for a multinomial problem, it's whatever the number of classes is. Maybe in fact, instead of using n, I should just say that, right? Just put the top number of classes. So that's what you're going to index over. Okay. So it's the probability of classifying a data point into class J when it does, in fact, belong to class J. So the idea is we're using probabilistic predictions for the classes. Now, let me point out, if you can always, if you're using, say, just class, like predicting to a class, so like you say we're doing binary classification and doing majority vote, right? You can always translate that to a probability, right? You're simply 100% probability for one class and 0% for the other. The whole idea of using probabilistic predictions is you can get more in between that if you want. But you can always translate majority vote or plurality vote into ones and zeros as the probabilities. Okay? So in particular, suppose p sub j, your algorithm predicts that p sub j equals 1. Okay? So you have an 100% probability of the correct class. Okay? So 100% of the time it's predicting into class 1, say, and class 2, it's getting them exactly right. Okay? So then what do you have? Well, negative pj log of pj for that value of j is equal to 0. So the base 2 log of 1 is 0. So that's 0. So there's no error, right? Okay. And in particular, why is there the negative sign on it? Well, the next bit will explain that. Why are we including a negative? If pj is small, so something close to 0, okay. So then what we're saying is we're predicting a small probability of being in the correct class, right? Then in that case, negative log base 2 of pj is very large, right? So the idea here is if we have a positive number close to 0, its base 2 logarithm is a large negative number. That's simply how logarithms behave. So the negative of that is a large positive number. Okay. And then it gets multiplied by pj, but the idea is that even though pj is small, it's much less consequential than the logarithm being large, right? So the whole idea is that logarithms, they're growing much faster than just the values of the p's themselves. Okay. So what that results in, the implication of this, is that we get a large error, negative pj times log base 2 of pj, because of the log part being so much bigger than the pj is small. So we get a large error for predicting a small probability for the correct class. So we said it was very unlikely a data point was in class J, but it actually is. And so we're saying, well, because of that, because we said we had a low probability prediction for it being in the right class, we're giving a big error for that. Okay. All right, so the point then is that cross entropy, once you've figured out that that's how it's working mathematically, it provides a very intuitive interpretation. the classification error. Specifically, high confidence in incorrect predictions is bad. Or equivalently, the way we've actually set it up in some sense is low confidence in correct predictions, right? But these are symmetric. One way to say it is that we had high confidence the data point wasn't in class J, but it actually is, right? So you can, this is all, there's a symmetry here between high confidence in incorrect and low confidence in correct mean the same thing. Okay, so that's a nice reason to use cross entropy because it interprets in a nice way. Okay, why not use cross entropy? Well, okay, so here's the formula. So what are we doing when we calculate cross entropy? We're computing a logarithm, a base 2 logarithm, and then taking a product, and then and then taking a sum. Okay. But the problem is a logarithm is a transcendental function. So this is our but here. What the issue is with this is the log base 2 function leads to high computational complexity. Because remember, we're not actually going to do any of this by hand. The computer is going to do all the work, right? And it's doing all of this in the background. We're not checking all of this up by hand as we go. It's all automated. Okay, and logs are difficult for computers to compute. They have to approximate them because they're a high-level transcendental function. They're not just some basic arithmetic operation. So to compute that log base 2, it does a bunch of approximation. And you might say, okay, but yeah, computers are super fast at computing that kind of thing. I can do log base 2 on my calculator pretty much instantly. Okay. But all of this adds up, right? When the algorithm is having to do enormous numbers of computations at every single step, all of that extra computational complexity eventually starts to add up together. Okay. So can we introduce something that works in a similar way, but maybe is easier to compute? Okay. And this results in the idea of the Gini index. Or AKA, the other name that gets used here is the Gini impurity. Okay. So this quantity, the Gini index, is given as follows. We take the sum over the number of classes. So we take the probability for the class and square it, and then we do 1 minus that sum. Okay. So computationally, this is much simpler than cross entropy. Because when doing the calculations with it, rather than having to compute base 2 logarithms, all we're doing is a square, which is just a multiplication. So we're doing a bunch of multiplications, adding a bunch of additions, and then a subtraction, right? So it's just basic arithmetic. It's much easier computationally for a computer to handle. Okay, but can we interpret it in a nice way? Okay. So the Gini index, what it does is it gives a measurement of what we might describe as node impurity, hence the other name Gini impurity, or node purity, I guess. what do we mean by node purity? So a small Gini value corresponds to most elements in the same node belonging to the same class. So in other words, what it's saying is that the target values as a classification problem at that node are all very similar. Okay. So here, let's take a look at a couple of extremes. Okay. So what happens if the Gini coefficient is 0 for a data point? Okay. Well, that means that the sum part is equal to 1. So we had 1 minus 1 equals 0. Okay. So what is that sum? It's the sum of a bunch of squares of probabilities. And the PJs, of course, all have to add up to 1 because that's the total probability. So in this case, you can check mathematically. The only way this can happen is if P sub j is equal to 1 for some j. And then all the others, P sub k, say, are 0 for k not equal to j. Okay. That's what would have to happen. Okay. I'm almost out of time, but let me just finish with one more example. On the other flip side of things, if the Gini index comes out to 0.5, this corresponds, as it turns out, to equal probability predictions across all classes. So in other words, you're not making very confident predictions, right? You kind of just don't know. You're throwing your hands up and saying, it's equally likely. We're predicting it's equally likely to be in any of the classes. Now, this is something else you can check mathematically, but let me just, to wrap things up, show you with in a binary example. So in binary classification, we can actually compute that we can see that this is the case. But the same thing goes up to generalizes to multinomial. Okay. So what we're saying here is we have a binary situation and we don't have any better probabilities than 50-50. So P1 is 0.5 and P2 is 0.5. Okay. So then P1 squared is 0.25 and similarly P2 squared is 0.25. And then the Gini index is given by 1 minus the sum of those squares, 0.25 plus 0.25, which is equal to 0.5. So that's in some sense then the extremes. Usually, of course, you'll land somewhere in between those, rather than making perfectly optimal predictions versus predictions that essentially give no information. They're just coin flips. Okay, so now that we've kind of set up the terminology and structure for decision trees, on Thursday, what we're going to do is work through a kind of an example to get a better idea of how they actually work, and we'll introduce some more of the ideas. How do we train a decision tree model, and what are the relevant factors that go into that, and in terms of creating an optimal model? So that's more decision tree stuff coming up on Thursday, and then we'll start to see what are some of the limitations to single decision trees, and how can we improve things.